Hello everyone. So in this video, we're going to look at the last mode of heat transfer, which is radiation. I very simplistically described heat radiation previously as just heat exchange that occurs between surfaces. And we're going to look at the definition together, but this radiation thermal exchange would occur if you have any objects that have temperatures above 0 Kelvin. And so, as we always do, let's start with the actual definition and then dig into the details. So, radiation is a mode of heat transfer in which energy is emitted by a surface due solely to its temperature. So, any substance at a temperature above absolute zero, emits thermal radiation. And radiation occurs regardless of the phase of matter. So, it could occur in solids, it could occur in liquids, and it could occur in gases. All of these would emit some sort of radiation if their temperature is above absolute zero. Also, unlike conduction and convection, radiation does not require a material medium. So when we looked at conduction, for instance, in solids, we said that there's vibrations and therefore you have this transfer of energy. Or when we looked at gases and liquids and tried to understand conduction in them, we said that you have random molecular motion and you also have collisions between molecules, and through that you get a net flux of energy transfer. And when we looked at convection, we said there's bulk motion of fluid over a solid surface or over a stationary surface, and therefore you have heat transfer. But radiation, on the other hand, does not require any material medium for heat transfer to occur. So what that means is that radiation could also occur in vacuum. And in fact, radiation heat transfer occurs most efficiently in a vacuum. This thermal radiation, it originates from microscopic energy transitions within matter. So you have inside matter, you have transitions that are associated with the electron configuration of the atoms and molecules, and the energy released during these transitions is transported away from the surface as electromagnetic waves, or alternatively photons. And this mechanism distinguishes radiation fundamentally from any molecular-based heat transfer process. Now, in comparison to conduction and convection, as I said, conduction and convection require a material medium. It depends on molecular collisions or bulk fluid motion. However, radiation requires no medium. It can occur through vacuum, like space. It could occur through gases, liquids, or solids. And this is why it is the most dominant mode of heat transfer when it comes to space applications. Okay, so let's understand some terms so that we can be able to quantify radiation in equations. So first, I want you to understand what surface emissive power means. Surface emissive power is just the rate at which radiation is emitted by a surface. And the units for it is energy watts per unit area, which is watts per meter squared. And this is called emissive power. This represents the total radiant energy leaving a surface due to thermal emission. So looking at this picture, you could see thermal energy radiation that is traveling through space from the sun, thermal energy radiation that's traveling through the air from the fire. Also, you'd have some thermal energy radiation that's traveling from the hand to its surroundings. Okay, so now let's look back at the definitions. In an ideal radiator, we call it a black body. So if you have black body radiation, that means the surface that you have is emitting the maximum possible radiation at a given temperature. And therefore, for a black body, the surface emissive power is found to be given by Stefan Boltzmann's law. What does Stefan Boltzmann law says? It says that the emissive power is equal to a constant, which is obviously called the Stefan Boltzmann constant, multiplied by the absolute surface temperature. So if you have any object, and if you want to calculate what's the absolute maximum this object can transfer heat through radiation, given its temperature, you can calculate that using this equation, but this assumes that this surface behaves as a black body, so it's an ideal radiator. And in real life, radiation from real surfaces would be a fraction of that. So that's why when we look at real engineering surfaces, they emit less radiation than the ideal black body at that same temperature. And that is why we have a concept of emissivity, which is essentially a measure of how efficient a surface emits radiation relative to a black body. So obviously the emissivity factor would be a range between 0 to 1, whereby when it is equal to 1, then you're dealing with a black body, or when the emissivity factor is less than 1, then it is a real surface, and the closer it is to 1, then the more power the surface is able to emit radiation, and the closer it is to 0, then the less emissive power this surface could emit power. Also, I want to note that the emissivity depends strongly on surface material and the surface finish, and it's not a bulk material property. In fact, it's a surface condition. And also, I want to highlight that this relationship highlights a strong fourth power dependence of radiation on temperature, because if you look at the surface emissive power of a black body is equal to the Stefan Boltzmann constant multiplied by the absolute temperature of the surface to the power of 4, which means that it's strongly correlated to the temperature of the surface. Okay, so now that we know how much radiation power, a surface would be able to give out, we need to now calculate or be able to figure out how much radiation a surface can receive. So in addition to emitting radiation, a surface may also receive radiation from its surroundings. The rate at which the radiation is incident on a surface per unit area is called irradiation. So irradiation G is how much radiation energy is incident on a surface. So let's say you have a solid surface, how much radiation is hitting the surface, that is called G. And how much radiation power is being emitted by the surface, that is called emissive power E. Okay, so let's focus about irradiation, which is the radiation power that's hitting a surface, that is called G, that is abbreviated as a G, and it's also in watts per meters squared. And that could be because of solar radiation or the hot flame that I showed you in just this previous example, or any hot surrounding surfaces really. So when you have radiation that's hitting on a surface, a portion or all of this incident radiation may be absorbed by the surface. And so we really care about just the absorbed radiation, because the absorbed radiation is what increases the thermal energy of the material. So the absorbed radiation per unit area is a fraction of the total irradiation on a surface. And that factor we call absorptivity. And so what happens is the portion of irradiation that's not absorbed by the surface, it can either be reflected or it can be transmitted, depending on the nature of the surface. Reflected and transmitted radiation, they do not contribute to the thermal energy rise of a surface. Now, I want to note that obviously absorptivity over here is just a fraction, similar to emissivity is a fraction from 0 to 1. So in terms of absorptivity, if it is 1, then that means that all of the incident radiation on the surface is actually absorbed by the surface itself, and so it would contribute to the thermal energy of the surface. But in reality, you could have somewhere between 0 and 1. So on the other extreme, if you have 0 absorptivity of the surface, that means that all of the incident radiation coming from the surroundings onto the surface itself is not being absorbed by the surface. And so in terms of thermal energy, it is negligible because it's not contributing to the surface thermal energy. Now, you might be wondering, what does absorptivity depend on? Well, it depends on the nature of the incident radiation. So that means what's the wavelengths, what's the source temperature. And also, just like with emissivity, depends on the surface material and condition. For example, you might have a surface that may absorb solar radiation very efficiently, but it could absorb thermal radiation from furnace walls less efficiently. Okay, so now that we understand we have two components to look at, which is the emissive power that a surface emits and the irradiation, which is the amount of power that a surface receives. And in order to calculate the net radiation heat flux, we need to find the difference between the radiation energy emitted, which is the surface emissive power by the surface, and the radiation energy absorbed by the surface from its surrounding. So if you look at this image, it kind of explains what I'm saying. You have irradiation that is being hit on a surface from the surroundings. A part of that is absorbed. And you also have emissive power that is being emitted by the surface. Now, the net of what's coming in and what's leaving, or what's leaving from what's coming in, would be how much net heat flux the surface is either gaining or the surface is emitting out to the surrounding. And so this would be the equation that you would use to figure out what is the net heat flux due to the impact of radiation on the surface. Now, a frequently encountered special case involves radiation exchange between usually a small surface at, let's say, a temperature Ts, and a much larger isothermal surface that completely surrounds the smaller one. So what do I mean? Let's say you have a small tank, or let's say you have some solids that are inside of a furnace. So in the case of when you have some solids inside a furnace, then the small surface would be the solid surface, and then the large isothermal surface would be the walls of a furnace that is surrounding the solids. Or let's say if you have another object inside of a room, and so in this case, the object could be the small surface with a temperature Ts, and the walls of a room could be the larger isothermal surface that completely surrounds the smaller one. Okay, so for this configuration, the irradiation incident on the small surface may be approximated as that of a black body at the temperature of the surrounding. So if you're trying to calculate how much energy is being incident on the object from the large surrounding, you could assume that it's a black body. So you could use the equation I showed you previously for black body irradiation. So in this case, you could assume that the total irradiation that's being incident on the object is Stefan Boltzmann's constant multiplied by the surroundings temperature to the power of 4. And if the surface is assumed to be gray, which means that the absorptivity can be equal to the emissivity, then the net radiation heat transfer equation, which I've presented here, could be simplified further into this equation, where you have the heat flux radiation, which is the heat flow over the area, surface area that's it being incident on, is equal to the emissivity times the Boltzmann constant times the surrounding temperature to the power of 4 minus the absorptivity multiplied by the irradiation power that is being hit on the surface. All that is equal to, now if you express the irradiation that's being hit on the surface as a black body irradiation, then you have G here is equal to Stefan Boltzmann's constant multiplied by the surrounding temperature to the power of 4, and therefore if you put that into this equation and simplify, you'll get that the heat transfer flux because of radiation is equal to the emissivity, because the emissivity and the absorptivity are the same. So let's just keep it as emissivity and pull that out, multiplied by Stefan Boltzmann's constant, because it is the same for both terms of this expression. Now multiplied by, the only difference is the temperature of the surface to the power of 4 minus the temperature of the surrounding to the power of 4. Now, for many engineering applications, it's convenient to express the net radiation heat transfer in a form analogous to convection. So in that case, you could express the radiation heat transfer by multiplying, obviously, the area with the heat flux, and that would give you the heat flow. But also, you could rewrite this equation, or you could express it in a way where you have the temperature dependence of to the power of 4 gets hidden in this radiation convection coefficient. And so if you want to use this equation, just make sure that the radiation heat transfer coefficient is now expressed in this formula. So the heat transfer radiation coefficient is the emissivity times the Stefan Boltzmann constant times the surface temperature plus the surrounding temperature multiplied by the surface temperature to the power of 2 plus the surrounding temperature to the power of 2. Now, it might be convenient for you to use this relationship, or it might not be. I just decided to show it to you anyways. And just remember that if you're going to use this radiation heat transfer coefficient, just remember that make sure that all of these assumptions apply to the situation that you are dealing with. And this concludes the high-level summary of radiation. And in the next video, we're going to look at an example of convection and radiation together. So without further ado, see you in the next video.